Hello, my name is Jana, and I'm going to take you through our project MakFleet. And this one mostly going to be based about border of motorbikes. And the type of contents I will have first the introduction, related works, problem statement, and many others as they are seen on the list. So from the background and introduction, this project bases mostly on border motorbikes or motorcycle taxi that we got the idea from. So primary micro mobile mode on campus, basically Makerere campus. So there's a high frequency and erratic routing or safety risks. And therefore we enter the basics that are needed. We have the spatial temporal data, whereby we need the GPS or accelerometer streams sampled every 5 seconds, and combines where spatial and when, that is temporal. And by the help of the knowledge graphs, the graph-based semantic warehouse, and where the nodes have the intersections of vehicles or drivers, and the edges whereby you can know where the events occurred, which which routes, and also the relationships between them, and also models like STGN, NN, the semantic awareness, privacy by design, the telemetry, epistemic trust, whereby there has the assurance that MakFleet's data and AI insights are credible, traceable, and also dependable for safety and fleet management decisions. And lastly, the micro mobility, whereby small or lightweight transport services are used for the short distance movement within and around the campus environment. So from the related works related to our project, there is from the year 2018 from UCAI, where they used STG ASEAN, and the results basically outperforms LSTM on MERT-R. And the architectural limitations from this paper, there is static graph, and they cannot handle the topology changes. And also the context limitation in this paper, city road sensors, and also not vehicle, the no vehicle level IoTs, and many other papers as you see here with different models with their architectural limitations and also contextual limitations. So when we go to the problem statement, basically what are we solving and what is the main issue that we are trying to bring out? So the domain application problem, border boards on Makerere campus operate with no formal monitoring. We just know, so we can know what's happening with them, the status, GPS or locations or what. So therefore, reckless driving incidents near student pedestrian zones go undetected. Also, the university administration lacks real-time safety intelligence or observations, and also demand surges, like basically rush hours, whereby they could cause unsafe overtaking or speeding, and also no data infrastructure that exists to enforce campus traffic policies. And the computational problem that we saw, the operational safety that involves the spatial temporal optimization, also like weak supervision, the use of through IoT telematics and OSM geospatial mapping, and also anomaly detection, reckless driving, together with demand forecasting, multivariate time series on spatial graphs, and continue learning across semester, concept drift, privacy preservations, uh, together with OOD robustness, edge to cloud streaming into this semantic knowledge graphs for flexibility and also scalability, and also the use of models like STG and then with the rule-based symbolic neurosymbolic architecture. Yeah, and among the research questions that led us to what we can do, basically our objectives, the research objectives first, to design and implement an ontology-driven spatial temporal knowledge graph for border fleet data on MakFleet University campus. Also to develop a semantic engineering pipeline that enriches raw IoT telemetry into meaningful campus events using HMM mapping, like map matching and rule-based classifications. Also to build and evaluate a custom spatial temporal graph neural network for reckless driving anomaly detection, also by receiving through alerts that or action alerts that appear on different dashboards, bring out such warnings by the help of the models. Also to detect a casual business intelligence dashboard that generates semantic subgraph explanations for flagged anomalies through alerts and many others. So among the research questions, we have what ontological schema best represents the spatial temporal relationships between border events, campus or topology and real-world behaviors. So basically here we would want to know also how accurately can semantic map matching and rule-based enrichment classify to IoT, classify the IoT telemetry into contextual, meaningful safety events. And last but not the least, what STGNN architecture behavior, robust anomaly detection and temporal, or like the semester under of temporal for the semester, and also the spatial for the campus zones, different campus zones around the campus, like how they are distributed or the shift between the distributions. Also, how can casual subgraph retrieval from the knowledge graph provide interpretable or actionable evidence for university safety administrators. So this research contributions and outputs by the help of the STG, the STGI data warehouse, we designed the first spatial temporal knowledge graph for campus macro mobile in Uganda, and also the semantic data engineering pipeline, where we built a 3-phase IoT pipeline, and also the custom STGNN with OOD protocols, where we developed a novel GCN with the LSTM architecture, which trained exclusively on semester 1 data, whereby we also use that data and evaluate on the semester 2 data or temporal OOD. And on the eastern campus zones with the special OOD. And lastly, the causal business intelligence dashboards, where we developed the first so semantic evidence generation platform for border safety, whereby flags or anomaly flags it trigger the 2-hop subgraph retrieval, and also rendering why a driver was flagged, so it can specify and administrators know why this happened. Also, the methodology and system architecture that we used the 3-phase semantic data engineering pipeline, whereby in the first phase we had the IoT ingestion and provenance, border IoT devices stream the GPS and accelerometer at 5 seconds interval. And in the first two semantic pipeline, whereby you had the HMM map matching snaps, where noisy GPS to OSM road edges, and in the last phase where we use the knowledge graphs and analytics by the use of by the help of different models to assess and have streamlined dashboards. And from the model one, we have the HMM map matching. The following steps occurred, where we had in step one the candidate selection by the help of the KD tree query, edges within altimeter radius. Step two, emission probability. Step three, transition probability. Step four, beta B decoding, and the output, whereby we had the matched edge U and matched edge V for the snap distance M and confidence score. And the mathematical formulation we have as there before. So model 2, the ST-GNN architecture and mathematical foundations that we used. In the architecture, we had an input where T had the 4 graph snapshots. We multiplied with that. And yeah, we had the input, whereby we used the spatial encoder, where we have the shared, or like we have it as shared, or like per snapshots, and the temporal aggregator, which is in per node, and also the output head, where we have the anomaly probability per node, and also the loss, where we have the weighted BCE, and lastly the optimizer. I have the Adam. Yeah, and the mathematical formulation is as below. Since time is running, I'll finish up quick. So from the dataset descriptions and explain EDAs. So we have the trip volume by by hour of the day, and the anomaly rate of hour by hour of the day. And with this, we have this source, which is the simulated overall MakFleet OSM road network by we used 15 border borders which are IoT equipped. And then from the records, you have ticks of 826,260 telemetry trips. From the semester 1 data records running from January up to April, to semester 2 records running from August to October. Use sampling of every 5 seconds per vehicle, and all that to acquire an anomaly rate of 8.8% of all the records. Peak hours, whereby at around 8 in the morning, where people are running for their lectures. And top anomaly was speeding, and it's the most frequent. And here we have the event type distribution, serenity score, the distribution anomaly, whereby with this we can know which event occurred mostly and at what rate, or like the count. And normal air travel occurred mostly. Speeding was one of the troubling event that happened with this a score of or a count of 63,222. And on the severity score distribution anomaly, also speeding exceeded the rest with a severity score of 0.8. Then driver risk profile. We have each profile scored against the risk, and these profiles these are drivers with for those vehicles, and the one with the most risk is Namutebi Sarah with almost a risk score of 1, and the one with the least is 7-year Ronald. And from the risk profile versus the anomaly rate, have those in red where they exceed the risk score, and they are at the peak of the anomaly rate also. So from the graph of speed distribution by semantic event type, you have the hash braking, which is a bit below the speed of 30, rapid acceleration also around 30, and speeding, the normal speeding, or like there was, okay, the speeding is over 40. And last but not the least, we have the event counts for semester 1 versus semester 2. And semester 1 exceeds semester 2, and when in the event mix, semester 1 versus semester 2, they're even. And then the last graphs, we have the accelerometer distribution by event type, as well as the map matching snap distance in meters. So with the results and according to the performance of the model, we see that we have the scores of the validation for the semester 1, the last 20%. We have the samples of 1,722, 28, and the temporal OOD for semester 2, samples of 5,757. So with the F1 scores of those are close to 1, which is a bit high and not bad. So benchmarking the performance as below, we see that expressibility in SS 1 is in spatial, and 2 for traffic density control, we say yes. Reckless driver, near zones, spatial. Casual chain traversal, no. And semantic. Yeah, we have the model selection and development, and then the model selection we have the STGNN plus the rule-based one, and the technical justifications why this model. The Gaussian inductive bias matches the spatial graph geometry of the campus and networking, and the scientific justification versus other alternatives. The random forest, this one lacks the spatial graph inductive bias. CNN, no relative structure. Standard LSTM ignores spatial message passing across road network edges. And the deployment pipeline from the telematics, the GPS, or the accelerometers through the 5-second stream to the provenance hashing through raw JSON-L, and to map matching, to also from that to semantic event enrichment, all those to the Streamlit causal also business intelligence dashboards. And the demonstration of the developed systems. Campus tab 1 has campus map, anomaly detection next, then causal evidence, and lastly the benchmarks. So database information involves 1 million of nodes, with very many, that of drivers, zebra crossings, provenance anchors, intersections, border stops, and many others. And the limitations that we face: no real border or GPS data collected. Simulations use OSM road topology with calibrated noise, and also model basically partial training, basically for only 10 over 50 epochs due to GPU constraints, and lastly the architecture or like strict campus graphs. And I would like to conclude by saying we successfully designed and implemented a spatial temporal graph, a knowledge graph for border fleet management, the first such system for campus micro mobile in Uganda. And also the semantic pipeline achieved 90.6% map matching confidence and correctly enriched 826,260 telemetric records into 6 semantic event types and many others. So based on these are also through the BI dashboards, it successfully answered why an anomaly was flagged on a certain sub-graph retrieval. Now, among the feature works, we plan to deploy a real IoT telematics unit on actual Makerere border, and extend campus or hotology to include passengers boarding and other events. These are the references that we used, and I also would like to acknowledge our supervisors, our Department of Computer Science, also the contributors of OpenStreetMap, and also the open source community. Thank you.